All right, so we've talked a little bit already about what strong and weak mean when we're talking about acids and bases, but we want to remind ourselves so we don't forget. It's not that this base is, or this acid is so strong, or this base is so strong it's going to kill Batman or melt your face off or something like that, right? When we're talking about strength of acids, all we're referring to is the degree to which the acid dissociates. Now remember, when an acid dissociates, it looks something like this. Let's call this acid HA. It's a generic acid. H at the beginning usually helps people indicate or realize that this is an acid we're dealing with. And the dissociation of an acid will be that hydrogen ion released and the rest of the compound being released with a negative charge. Okay? If this HA is a strong acid, then you put it into water and H and A will never come back together again. All right? They'll always stay separate because that's the definition of a strong acid. If it's a weak acid, so I can say strong acid here. If H, some other generic acid we'll call HX, is a weak acid, then we can draw it with two arrows to show that, yes, it dissociates, but the resulting products come back together. So there's one way that we can indicate with our writing that something is a strong or a weak acid. Okay? Now, the strong acids, there's only 7. And this is the list here. HCl, HClO3, HClO4, HNO3, HBr, HI, H2SO4. Okay? And I want you to write down this list of strong acids on the back of your periodic table or on the front of your periodic table, somewhere where you can refer to them always. Okay? This list of strong acids is just something that we're going to have to kind of become familiar with gradually. Okay? And our method of determining whether an acid is a strong acid is unfortunately as simple as, is it on our list of strong acids for now? Okay? Strong bases, as we mentioned previously, they are group 1 hydroxides, so ionic compounds that contain hydroxides that contain metals from group 1A, which are our alkali metals, or calcium, barium, and strontium. Okay? And that means compounds, ionic, that contain hydroxide ion, when placed in water, they'll release that hydroxide ion. So a little cartoon here to help us think more about what's going on when you have a strong acid. The strong acid interacts with water and all of it releases a proton, 2 water molecules, and results in the free counter ion, which in this case is the chloride ion. In a weak acid scenario, only a very small amount of our material will dissociate. There will be some dissociation. Some of the hydrogen ion will go onto water and form the H3O plus ion, and the resulting counter ion, in this case this is acetic acid, so this is the acetate ion, only a small amount will be present. And we include a second arrow there to show that these two will go back very quickly. But as soon as they go back, there will be another one at the same time going forward. So at any one moment in time, there is an amount of dissociated acid here, but it is not a significant amount. Okay? All right. Weak acids only result in a small amount of current being able to pass through solution, or in other words, the conductivity of solutions that contain weak acids and weak bases is minimal. Like strong acids, they will completely dissociate, and strong electrolytes, right? So they'll result in a conductive solution. Now, we're going to teach you how to name acids. Acids are named 2 ways. One are based on whether there are 2 different kinds of acid. One kind of acid is what we call a binary acid. A binary acid contains just the hydrogen ion and one other kind of element. It doesn't need to be just one element, like H2S is an example of a binary acid. It just contains one other element, which is a sulfur. So HCl, H2S. These are binary acids, and they're named following this model. You could say hydro, and then you fill in the blank here with the name of your counter ion. Here in this case it's the chloride ion. Here it's the sulfide ion. And you end it with ic acid. So hydrochloric acid. So this binary method is, I call the hydroblankic method for naming acids, right? The other method for naming acids is the other group of acids is called oxoacids because they contain oxygen. So if an acid contains oxygen, then what you do is, and these acids will also be acids that contain one of our polyatomic ions. So if you have your polyatomic ion chart and you look at any anion on the list, what's an anion?
Anion, that's the negative charged ones, right?
That's right. So any polyatomic ion with an anion, -1, -2 charges, -3 charges, any one of these, if you give the appropriate number of hydrogen ions, whatever the charge is, it can become an acid. And that's what our oxoacids are, and that's also how we name them, based on the polyatomic ion that they are made of. So, if the polyatomic ion, in this case, this is the nitrate ion, hydrogen with the nitrate. If if the polyatomic ion ends in ate, then the acid ends in ic. So nitrate will come together with hydrogen to form nitric acid. Sulfate forms sulfuric acid. They throw a little R in there for us for the sulfur, sulfuric acid. Chlorite, if the polyatomic ion ends in ite, not ate, but ite, then the acid ends in us, chlorous acid, phosphorus acid for phosphite ion, right? So, polyatomic ions end in either ate or ite, and ate goes to ic, and ite goes to us. That's a little phrase that you remember. You keep above your bed, and every time you wake up in the morning, you say it to yourself 3 times. Ate goes to ic, ite goes to us. Ate goes to ic, ite goes to us, right? And if you say that, then you'll always remember how to name your oxyacids. Okay? So let's see what you got. Which of the following is named as this hydroblankic acid?
Which one is named or not named?
Oh, not named. Sorry, which one is not named?
So there were 2 kinds of acids?
That's right. There's 2 kinds of acids. What were the 2 kinds? Do you remember?
I don't remember.
Binary and...
Oh, oxoacids.
That's right. Binary and oxoacids. Binary acids. Of this list, which ones are binary?
A is binary and D is B also?
Yes, B is also, because it just has one other kind of element. Now, what about C? Is C a binary acid?
No, it's an oxoacid.
Very good, oxoacid. That means that C is not named the same way as the other ones, right? And which one is it, the hydroblankic model?
That's the binary acids.
Very good, binary acids. So which ones will be named binary style, hydroblankic?
Which ones will?
Yeah.
A, B, and D.
Very good. And so C is not going to be named after the hydroblankic model because it's an oxoacid. Excellent. So let's see how we do. HNO2, what's its name?
Do you have the polyatomic ion chart?
Yes, let's get the polyatomic ion chart over here.
I don't see it. Oh, there it is, nitrite. So that's nitrite. Ite goes to ic, right?
No, 8 goes to ic, ite goes to us.
Oh, so nitrous acid.
Very good, nitrous acid. How about this one, HClO4?
ClO4, I don't... Oh, there it is. perchloric acid.
Very good. 8 goes to ic, perchloric acid. HF.
Oh, it's not on the, hydrofluoric acid.
Very good. Hydrofluoric acid. It's the binary acid, so it's named hydroblankic, right? Hydroblankic model. Very good. HMNO4, should we give the folks at home a chance?
Yeah.
Okay, make sure you answer the question, then push pause, answer the question, come on back. Okay, ready? Give it to him, Fred.
Permangonic acid.
Okay, permanganic acid. Very good. Permanganic acid. All right, H2CO3. Folks at home, give it a shot. Okay, tell him, Frank, or Fred. Tell him, Fred.
You forgot my name?
I'm sorry, I was thinking of permanganic, and the Frank came out. I don't know why. Okay.
Can't believe you forgot my name.
I know. I'm sorry.
Well, that's carbonic acid.
Yeah, carbonic acid. Very good. All right. Good job. You're naming the acids wonderfully. Okay. That's a good place to stop. We'll use that next question as a review next time.